Welcome to the talk. In today's presentation, I'll present our paper, which is DCSHARP, 3D Gaussian Splatting with Direction Cosine Spherical Harmonics and Shape-Aware Pruning. So let's start with the overview and benefits of 3D Gaussian Splatting. So 3D GS offers 3D scene generation from 2D images information. It starts from structure of motion, point cloud, and learn the 3D Gaussian parameters. And then in 3D GS, we have a differentiable rasterizer that splat the learned Gaussians on screen to generate 3D scenes. And then it involves learnable parameters like mean covariance of each Gaussian along with the color features. And for the color features, it uses spherical harmonics to compute the color of each pixel location for the generated 3D scene. So there are benefits of 3D Gaussian splatting that involves high FPS, more than 200 for dynamic scenes, and it offers high training speed to train a Gaussian model for a single scene. Apart from the benefits, there are some challenges of 3D Gaussian splatting. First one is high learnability. So it involves more than 1 million Gaussians for a complex 3D scene. And then it has a low frequency bias for spherical harmonics for color computation. So 3D GS uses spherical harmonics for color computation, and spherical harmonics degree 3 misses high frequency details, particularly in specular or anisotropic lighting conditions. Finally, so 3D require memory around 800 MB to store the Gaussians locally, which are used for the rasterization. And all of those stored Gaussians are in high precision that involves high precision metrics and scalar operations to compute the color and performance for the rasterization. Due to these constraints, 3DGS are limited to GPUs due to high resource requirement. So these challenges motivate us for the resource efficient 3D Gaussian splatting. Mainly, we have two motivations. So first one is high performance 3D GS, where we aim to improve 3D GS to capture high frequency details of complex 3D scenes. For this purpose, we introduce spherical harmonics with direction cosine modulation. This offers better 3D GS to capture the specular and anisotropic lighting in complex environments. Then second motivation is resource efficient 3D GS, where we aim to prune a 3D Gaussians to render 3D scene with minimum resource utilization. This offers limited Gaussians that comes with the benefit of low learnability, computation, and memory utilization. So for the first motivation, we replace the conventional spherical harmonics function with direction cosine spherical harmonics. We apply DCSH that maps spherical coordinates of spherical harmonics to Cartesian-like directional coordinates. So we apply this mapping considering our rotation matrix, which is developed based on the direction cosines alpha, beta, and gamma. And then this rotation matrix also help us to update the coefficients of spherical harmonics function that is used in the color computation along with the learned color features during the Gaussian learning. And then with those updated spherical harmonics, we compute the colors for each of single spherical harmonics degree with in our direction cosine spherical harmonics mapping. So in this way, considering the third degree of spherical harmonics, the direction cosine spherical harmonics captures the high frequency details without increasing the spherical harmonics degree that involves high computation. So basically, we update the coefficients of spherical harmonics and apply a modulation strength based on the spherical direction cosines that actually help us to capture high frequency details. For the second most motivation, which is resource optimal 3D Gaussian splatting, which is based on shape-aware pruning, we consider shape of the Gaussian as a pruning parameter. We got this motivation by considering the challenges of prior works that involves opacity magnitude based pruning, which is rigorous and that only considers the size of the Gaussian in terms of its magnitude. And then the second trend of pruning is pseudo rendering that involves high compute and also degrade the performance. Considering these challenges of prior works, we choose scale gradient based pruning, and for this purpose, we first observe that the Gaussian formation is mainly dependent on the covariance that involves scale and rotation, which are the learnable parameters. So scale decides the shape of the Gaussian. So we prune the redundant Gaussian based on the iterative gradient update of the scale. We choose scale as a pruning threshold to prune the redundant Gaussians without any significant drop in the performance. So for that purpose, we first look at the profile of the scale gradient and verify the scale threshold that we need to choose to prune the Gaussians. And in this effort, during the training stage, we save the gradient after 10K iterations So for we save the gradient for multiple iteration, let's say 12K or 15K, and then in those iterations, we observe that the gradients are low for most of the Gaussians. So which employs the low learnability and the contribution. So all of those Gaussians with low gradients offers low learnability and are safe to prune. So we observe that during the training stage, most of the Gaussians, around 65 to 70%, have very small gradient value and they are not iteratively changing over multiple iterations. So that gives us the confidence to prune all of those Gaussians with very small gradient value and also any iterative update safely without losing the performance. And only active Gaussians which are having a significant gradient value and also a continuous update over the training duration are actually contributing to the color computation for the final scene generation. So it is a complete flow of our DCSH and DCSH ARP 3DGS. So we first start with the iterative pruning where we store the scale gradient locally and iteratively compare the gradient and update the generated mask. And then we apply those generated masks on the active Gaussians to reduce the active Gaussians and remove the redundant Gaussians. So in this way, we get twofold benefit. One is our training speed is improved, and second is basically we are reducing the training resources and we are eliminating the redundant Gaussians. Finally, we get a pool of active Gaussians and then we compute the color for those only those active Gaussians based on direction cosine spherical harmonics, which is modulated spherical harmonics. And then based on that, we splat a 3D scene and then compute the L1 loss between the rasterized and actual image and update the active Gaussians with Adam step during the training stage. Now I'll talk about the performance of 3DGS with DCSH and also with DCSH ARP. So the training strategy for DCSH is standard or as of 3DGS using L1 loss and Adam optimizer. And we evaluate the performance on different SOTA 3DGS datasets. Then we also compare the performance of DCSH with existing 3DGS SOTA works. And for the evaluation purpose, we use PSNR, SSIM, and LPIPS evaluation matrices, which are the standard 3DGS evaluation matrices. We observed that quantitatively 3DGS improves PSNR by 0.23 dB, SSIM by 0.08, and LPIPS score by 0.034 in comparison to state-of-the-art 3DGS works. And qualitatively, we observed that 3DGS with direction cosine spherical harmonics improves the rendering quality on speculative or lightning conditions, particularly if we see this chunk of the image. So we observe that vanilla 3DGS blur out the lightning part, but DCSH based 3DGS captures the fine-grained lightning details pretty well. Then we also compare the performance of DCSH ARP, which is 3DGS with shape-aware pruning with SOTA 3DGS pruning works. So we observe that in comparison to the recent state-of-the-art light Gaussian LP 3DGS based pruning works, our DCSH ARP improves PSNR by 0.5 dB, SSIM by 0.01, and reduces the LPIPS up to 0.06. On top of that, 3DGS reduces number of Gaussians by up to 4x without losing the performance. And overall, from end to end, it reduces the memory consumption by 1.7x and training time is reduced up to 4 minutes. Additionally, we also change the pruning ratio to observe the resilience of 3DGS ARP in comparison to the SOTA pruning strategies like opacity magnitude based pruning or pseudo rendering with learnable mass. So we observe that DCSH ARP seems more resilient with higher pruning ratios in terms of all three scores. We also compare the performance of 3DGS qualitatively, and for this purpose, we consider both indoor and outdoor scenes, and we also consider real-time human avatar dataset. So, in comparison to 3DGS, our DCSH approach captures the textures in better way for indoor scenes with and without lighting conditions. Then for the human avatar case, we observe that 3DGS with direction cosine spherical harmonics captures the fine-grained details near the hair regions and offers higher quality in comparison to the conventional spherical harmonics based 3DGS. Finally, I'll conclude my presentation. So we implemented direction cosine spherical harmonics to replace the conventional spherical harmonics for high quality 3D rendering and to capture the anisotropic and specular lightning details. In this case, with direction modulation, help improve the 3D rendering quality with minimum number of Gaussians. On top of that, we prune non-salient Gaussians to unlock the potential of on-device 3D rendering, for example, in AR/VR devices. For this purpose, our proposed shape-aware pruning method with DCSH enables pruning on the fly while achieving high throughput with zero 3D scene rendering quality degradation for complex scenes. So DCSH ARP with 4x less number of Gaussians and 1.7x less memory requirement generates high quality novel views with high FPS. Thank you so much.